going to produce a T-joint using electrical wire. Now, T-joint is a strong, mechanically strong joint that allows us to join heavier duty pieces of wire together to make a long-lasting joint, provided we're not exposing it to high levels of vibration. There shouldn't be any significant problems, and this should last for years and be highly electrically conductive. First of all, what I've done is carefully, in the section of the continuous wire that we already have in place, I've removed some of the insulation. This is probably the most time-consuming component of actually doing this. It takes a little while to get it right. Make sure you don't cut any of the conductors. I've just applied a gentle twist in the direction of the lays, and the lays are the natural twisting that the wires have when it's being manufactured. If I look at it from this direction, they're twisted in a clockwise motion, and you'll tend to find that's kind of the natural position for them. What I've also done is the wire we're going to add to it, which in this case will be this blue wire. I've stripped the same length of insulation off, so I've got an equal length of conductor exposed, and that is what we're going to be able to join onto here to give us a mechanically very strong joint. Okay, next up I need to prepare the wire. First thing I'm going to do is I'm going to take just 3 strands. Bit fiddly, there's 2, one more, there we are, 3 strands. And I'm just going to lay them to one side, bend them out of the way, they'll stay in position. Now I want, what I could do, if I'm doing this really properly and accurate, I would count the number of strands that we've got here, and then obviously divide it so we have an equal number of strands on both sides. I won't bore you by doing that. I'll just roughly divide them, but we should technically be using equal number of strands on both sides. Again, I'm going to now just twist them to form their natural lays, which can be a little bit fiddly at first until you get them going. Here we go. It's only a gentle twist. We should find if you over twist wire, what will happen is the thickness will actually start to get bigger and the length will reduce, because as you're twisting them they're all gathering together in one small area. So we don't want to do that. Just going to put another twist on them. Nice gentle twist. So they're just held together quite nicely. Now what we're going to do with these 3 strands that we've got here is we're going to use those as a little bit of whipping. So again, I'm just going to put that twist on them. So I've got 1 3-ply, fiddly this one, 1 3-ply strand. There we go. And then what we can do, just bring those 2 together, and in the same clockwise directions we had before, I'm just going to do what's called whipping. So we just run around and around and around, and we just keep working it around, keeping it nice and tight. Try not to lay it on top of each other, try and keep the gaps fairly close together. This gives us reinforcement, it strengthens the whole thing and prevents these 2 wires from splitting apart. I want that nice and tight, just do that by hand. And now I have 2 strands which are held together, locked in place by a nicely whipped little reinforcement at the bottom. I've got no strands sticking out, they're going to stab me while I'm working on the fixture. Now what we need to do is introduce them into the main conductor and start to get them to join forces with that so that we can solder it all together. So place that nicely in the middle, and then what we're going to do is I'm going to take this first strand that we've got here, hold the other one in position, and I'm going to twist it so that it starts to wrap around our existing conductor. Keeping it again nice and tight. Try not to bunch up too much. and then the tails, just the loose bits at the end, just make sure they're nice and tight in there. That's that side whipped, and as you can see that's formed on there quite nicely. Then do the same, and this one's going in the opposite direction. It's not perfect. I've kind of deviated from the middle a bit. I've got a little bit of exposed end there where it's not fully wrapped, but we're pretty much there. So mechanically that already is pretty good. Conductively it's not bad. It'll break down over time because the copper will start to oxidize, and once the copper oxidizes you get much less conduction. So now what we need to do is solder them together. So soldering, I mean, it's a lesson in and of itself. Soldering iron is up to temperature, it's clean. So I've just wiped it off on one of the nice metal cleaning pads. You can also use a damp sponge, whichever you prefer. The most critical thing when you're soldering is if you try and solder dry. If I use this soldering iron now and I apply that to material, what will happen is it will take forever to heat up. Because you've got a dry hard surface on a dry hard surface, our point of contact is negligible. A couple of tiny strands will get warmed up and it will take forever, and what will end up happening is the whole wire will get hot and all the insulation will melt off and it'll be a mess. Instead I want to speed up heat transfer to be as quick as possible, and to do that what I need to do is make sure that the tip of the soldering iron is nicely wetted with a nice big glob of solder. So now when I bring that into contact, I'm getting, and you can actually see it's actually forming around the metal, I'm getting good heat transfer, and then after a couple of seconds I can start to just apply a bit of solder, making contact with the liquid solder that's already there, working my way along, stopping before I get to the end so I don't damage the insulation too much, work my way along. And you can see how readily that just falls into place, and then just reinforce the T-bit and the bottom, keeping the tip nicely moistened. There we go. That's pretty much there. You'll notice on the left hand end I've got a big lump. I'm just going to get rid of that. I'll just heat that up and give it a little flick. Might need to do it a couple of times. There we go. Didn't touch the hot area at all, just flicked on the blue wire here a little bit further down, and while it's molten it'll just drop off harmlessly onto your bench. That is now a nice fully soldered joint, which is mechanically very, very strong. So T-joint has quite a lot of advantages. We've now got that split in the wiring, so we can now have current going in two directions, which is very useful. It's not unusual to need to kind of take a spur off, perhaps a power line to run a secondary relay or something along those lines. This gives us the ability to do that and makes for a very strong joint. T-joint has a disadvantage. It's quite tricky to insulate. If you try and get heat shrink sleeving over this, well, it's nigh on impossible because we've got this spur coming off the side, and because it's soldered it becomes quite rigid and it's quite difficult. You can, but it's quite difficult to bend that down, but you can get it to run flat if you don't put too much solder on there, and then we could insulate that. The advantage of this is it keeps the thickness nice and uniform. I can put some heat shrink over there and I won't end up with a great big fat bulge in the wire that we can using some other methods of joining. So that's the T-joint. Now the question is, what happens if I just need to join two pieces of wire together? So in this scenario we've got to join two pieces of wire together. I'm using different colours because it just makes it stand out a little bit better on the filming, but in reality obviously you would probably be using identical colours. We need to connect these two together. There's a million and one ways we can do it. What we're going to look at here is a prescribed method that's called a marriage joint. The marriage joint is there because it provides an exceptionally strong, mechanically strong, yet again, joint. So not something that's going to easily come apart, and it provides very good conductivity by virtue of being a soldered joint, which means there's less likely for oxidation on the copper, which means it will continue to be as conductive as the copper itself, even though it's a joint between two different pieces of wire. What we've done, I've stripped about 50mm from each of the two conductors, and the first task that I need to perform is to take the conductors and twist them halfway along, about 25mm, 20-25mm, quite firmly but in their natural direction of lay. So just twisting the wire and being quite aggressive with it, just to about halfway to about there, making it nice and tight. So one side and the other about the same. It's important to make sure all these strands are nice and straight before you start this. You don't want this to be a bird's nest, nice and natural, just as they came straight out of the insulation. Should look something like that, so they're all nice and straight. So you don't need to get a rule out to check these, just make sure they're roughly about right. So we've now got two of these little sets of conductors. Half of it's strongly twisted and the other half is just the open conductors slightly splayed out. And what I now need to do is quite carefully, and this can be quite time consuming, I won't film the whole thing, but I'm just going to slowly start to tease these apart to make, if you like, a brush. So what we should be able to achieve is we can lock the two together. Ideally it should be that one strand from the right hand wire should be surrounded by two strands from the left hand wire, and you end up with kind of bird's nest that looks a little bit like this. And once we've got that, we can start to just smooth them all down. So if any just kinked out, just make sure they're all nicely pushed back in so they can lay nice and flat. And then once we've got them in and nice and tucked up inside next to each other, I'm just going to take these ones, which are from my left hand wire. I'm just going to start to twist them in the natural clockwise lay direction, round and round and round. And once I've got them nice and tight, I'll do the same with the strands from the right hand cable. I'll twist them round and round and round till we get them nice and tight. If there's any loose or dubious looking ones, just make sure you go round and round. Depending on the thickness of the conductors that you're using, you might actually need to finish this with pliers, because hands will not be enough to get them down really tight. And just have a good inspection of them, make sure it looks fairly clean, fairly smooth, fairly flat. It should be no thicker than the conductor. By the time it's finished, you should have no significant high spots. You might get a few just on the end. You can just clean those up a little bit. But the finished product should look something like that. And now we're ready to solder it. Okay, so I've got my soldering iron nice and hot. Nice and clean tip again, and as always the key is the tip must be loaded with solder before we even start. I tend to start in the middle, just let the bubble of solder just sink its heat into the work, and then once that starts to flow, just work my way along, just adding small amounts of solder, keeping the tip of the soldering iron nice and moist right the way to the end. Give it a flick to finish. It's fallen over, doesn't matter. Again, just preload it. Couple of seconds just to get the heat in, and then we just work our way along, dribbling the solder in. Don't get right onto the end because you'll melt the insulation. Always just give it a little flick at the end. Get any large bits of solder, they'll just fall off onto the bench, and we've got our joint completed. When you've done, just make sure you rotate it round, make sure you haven't got any spots where the solder's not flowed all the way through, so the copper is fully encased in solder, which gives us a perfect joint. We've avoided going right up to the ends, which would cause the insulator to get blackened and melted. It would swell up and make an unsightly mess that could potentially allow water to get through, or will at least keep our finished wire a little bit fatter than we'd like it to be. Some heat shrink over the top of that, shrunk down, would then make for a perfectly secure and potentially watertight joint that will last for ages. So you might ask why it is we don't use solder joints more often, because they're not everywhere. They do have a significant problem. Solder, because it goes quite hard, becomes very weak, and it's prone to failure due to stress. So if we have this particular joint, this T-joint that we made earlier, in a high stress situation, it's getting a lot of vibrations perhaps, it's not in a particularly nice environment, and you might find this wire gets moved from side to side. Because of the stiffness we've engineered in with the solder, it actually doesn't take too long until that happens. The mere fact that by losing that flexibility we had here by putting the solder in has made it really prone to failure. So solder is a fantastic solution if it's used in the right situation. But anywhere you're in any high vibrations, high loading kind of situation, it's often not the best option for you to be using. So if we're not using soldering, how are we going to make our connections? One of the most common methods of making electrical connections is these things. Crimp connectors. Small, and I say small because there are hundreds of different styles. This is just from my carry pot that I have. It just allows me to take some of these with me in different jobs and applications. These crimp connectors are incredibly useful, incredibly flexible, lots of different options in a relatively small kind of package. We have, well, at the bottom here we've got an eyelet. This is useful for making screw connections, connections to power terminals, etc. The red ones are the smallest you can get, so they are quite small in terms of conductor size, be ideal for this kind of wire. Here we've got a joiner. Now this is the medium size, slightly bigger conductors. This has a hole either end, and what that does is that would allow you to strip the insulation off and crimp these two wires together to replace that married joint very much easier, and without that problem of the lack of flexibility of a solder joint. These are actually designed to allow the wires to flex a little. They can deal a lot more with high stress, high vibration situations. And there's a couple of spades, two different size spade connectors. This one's fully insulated. These are really useful because obviously you don't need to worry about any insulation on them. The exposed conductors are fully covered, so you can put these in without any extra protection. This one is a non-insulated. This will be better to do the demonstration on. They're fairly simple to install, but they're also very easy to get wrong, and lots of people get them wrong. So we're just going to go through crimping this connector onto the brown piece of wire here. So I've stripped the insulation off camera. I've twisted it to its natural lay in the clockwise direction. I've cut off too much, as you can see. It's way too long. So I need to shorten it now, and what I need to do is to be able to get it so that when I insert it in to the connector, you'll just see the little bit of exposed copper protruding from the very end of the insulated sleeve. That's really important. That's what we call the beard. We call it the beard because it tends to go a bit sort of bristly when the conductor has been squished and the connection has been made. What happens is internally to here the metal is collapsed down, it's shrunk down and it's formed around the wire. So the wire is compressed and it's held really tightly. But because we have the little beard sticking out, we actually have a little bit outside of that compressed metal which is bigger, that hasn't been shrunk down. Because of that, there would be no way you could pull that connector off. It's firmly, securely connected to the spade connector and the wire. And it's not going anywhere. So what I need to do is be able to do that, but I also need to make sure that there is no exposed conductor here sticking out of the insulated part of the terminal. So I'm going to need to shorten it. It's fairly straightforward. You can kind of see I need to take about, well, this can go in quite a ways, take about that much off. We want to make sure the insulation is right up inside the conductor connector, and that's perfect. So there you can see just got a tiny little bit of the copper beard showing, and there's no conductor showing at the end of our terminal we're ready to crimp. This rather sorry looking piece of equipment is the ratchet type crimping tool that's used for these connectors. We can see it's for these connectors because it has the 3 coloured dots. We've got the yellow dot, we've got the blue dot, and we've got the red dot, and that corresponds to the 3 sizes of these crimp type connectors that we can get our hands on. They're different sizes. You must use the right colour in the right hole. You nearly always find that the smallest one, the red one, is at the front, and it works back towards the yellow one at the back, which is the largest. You can also get other types, this kind of crimper. Now this is actually for a non-insulated type, but it does have the facility with these little cutouts down here to do the yellow, the blue and the red, and it will provide some kind of crimping. Avoid these like the plague. Actually this end is exceptionally good. For the non-insulated ones that we're not covering here, this is fantastic. But for the insulated connectors like the ones we're using now, this kind of thing is appalling. It's nowhere near strong enough, and it doesn't compress the connector properly to make a good joint. So if we get those, always want to be using the proper ratchet type. And by ratchet type, what I mean is when you start to squeeze them and you start to compress the fitting, there is a ratchet just down here which you can see click every time I squeeze it. Now that's job is to prevent you from removing the connector until you've compressed it hard enough to make a good joint. So I can't open this back up. As you see, it will not move until I go right the way down, and you hear it click, and then you can let it go. These make a guaranteed really strong joint if we assemble it correctly, if we prepare the wire properly so that we have the setup as we've just shown you. Using these will be perfect. Okay, so I've got the connector installed. I like to keep them nice and level so it's in line with the jaws, and that keeps it nice and flat when it's all crimped together, otherwise you get a bulging unsightly connector. I've got that little bit of wire sticking out, and I've got the wire nice and firmly inserted in, and the insulation is perfect. I can't see any bare conductors, and then all we need to do is squeeze. Then you hear a little click, and that little click tells us that when I release it, I've got slightly bent out of position, straighten that up, but I've got a doubly crimped. See, there's 2 squashed areas on there, so the wire is held firmly in place. One here holding the beard. This one has actually come down and also caught the insulation, which means mechanically that's incredibly strong. There's no way you'll pull that out of there. But because it's crimped it in the correct fashion, this is able to move from side to side without there being any issues of that rigidity we saw with the soldered joint. Let's just get a close up and see what the crimping looks like. So if it's the correct tool, like the one we've just used, you'll actually just be able to make out here we've actually got a number in there which signifies the size of the crimping tool that's been used. That means if you're ever fault finding, you ever trying to find out why you've had a failure on the machine, this is an actual record that shows you which size jaws have been used when this was assembled. We've got a relatively speaking nice thin profile. It's not going to be bulging out, sticking out too much, and it's in line with the direction of the spade. So this is a perfectly crimped connector ready for installation into the machine. If you follow those procedures every time you use those, you will not go wrong, providing you're always using the correct machinery to form the crimps.